7.1 Ion formation. The objectives of this lesson are to define a chemical bond, describe the formation of a positive and negative ions, relate ion formation to electron configuration. Some vocabulary you might want to review is octet rule, and some new vocabulary you'll come across is chemical bond, cation, and anion. Imagine going on a scuba dive, diving below the ocean's surface and observing the awe-inspiring world below. You might explore the colorful and exotic organisms teeming around a coral reef. The coral is formed from a compound called calcium carbonate, which is just one of thousands of compounds found on Earth. How do so many compounds form from the relatively few elements known to exist? The answer to this question involves the electron structure of atoms and the nature of the forces between atoms. In previous chapters, you learned that elements within a group on the periodic table have similar properties. Many of these properties depend on the number of valence electrons the atom has. These valence electrons are involved in the formation of chemical bonds between two atoms. A chemical bond is the force that holds two atoms together. Chemical bonds can form by the attraction between the positive nucleus of one atom and the negative electrons of another atom, or by the attraction between positive and negative ions. This chapter discusses chemical bonds formed by ions, atoms that have acquired a positive or negative charge. In the next chapter, you will learn about bonds that form from the sharing of electrons. Recall from previous chapters that an electron dot structure is a type of diagram used to keep track of valence electrons. Electron dot structures are especially helpful when used to illustrate the formation of chemical bonds. In Table 7.1 above shows several examples of electron dot structures. For example, carbon with an electron configuration of 1s2, 2s2, 2p2 has 4 electrons in the second energy level. These valence electrons are represented by 4 dots around the symbol C in the table. And again, if we look at this table, we can go ahead and see, right, lithium has 1 valence electron, beryllium has 2 valence electrons, boron has 3, carbon 4, nitrogen has 5, oxygen 6, fluorine 7, and neon 8. If we go ahead and just kind of look at the periodic table, right, we were talking about in previous lessons, that everything in the same group, in the same family, have the same amount of valence electrons. Right, everything in the first group has 1 valence electron: hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Everything in group 2 has 2 valence electrons. Everything in group 13 has 3 valence electrons: boron, aluminum, gallium, so on and so forth. All right, with the exception of helium. Helium has 2 valence electrons, but every other noble gas has 8. Right? And the periodic table is set up in such a way that so that we can actually go ahead and use this as a tool to go ahead and interpret how many valence electrons do these atoms have. Also recall that ionization energy refers to how easily an atom loses an electron, and that electron affinity indicates how much attraction an atom has for electrons. Noble gases, which have high ionization energies and low electron affinities, show a great lack of chemical reactivity. Other elements on the periodic table react with each other, forming numerous compounds. The difference in reactivity is directly related to the valence electrons. The difference in reactivity involves the octet, the stable arrangement of 8 valence electrons in the outer energy level. Unreactive noble gases have electron configurations that have full outermost energy level. This level is filled with 2 electrons for helium, 1s2, and 8 electrons for other noble gases, which can be represented as ns2, np6, where n is that energy level 1, 2, 3, 4, 5, 6, or 7. Elements tend to react to acquire the stable electron configuration of a noble gas, and that's important here, right? Every element wants to become that of a noble gas. A positive ion forms when an atom loses one or more valence electrons in order to attain a noble gas configuration. A positive charged ion is called a cation. To understand the formation of a positive ion, compare the electron configuration of the noble gas neon, atomic number 10, and the alkali metal sodium with the atomic number 11. Note that the sodium atom has one 3s valence electron. It differs from the noble gas neon by that single valence electron. When sodium loses this outer valence electron, the resulting electron configuration is identical to that of neon. And if you go ahead and take a look at figure 7.2, it shows how a sodium ion loses its valence electron to become a sodium cation. Right? So here we have this sodium, this neutral sodium atom, right? It has 11 protons, that's how we know it's sodium, and 11 electrons, right? Now those electrons can go ahead and change, right? So what's unique is that when we have some sort of amount of energy coming in, right, in which we call our ionization energy, which in this case it is 498 kilojoules per mole, when this amount of energy comes in and hits that neutral sodium atom, right? Bam! Right? Sodium loses that electron, right? Still 11 protons. However, now only has 10 electrons, right? And we get this sodium cation, right? By losing an electron, the sodium atom acquires that stable outer electron configuration of neon, right? It has that 10 electrons, just as neon has those 10 electrons. So by losing an electron, it now acquires that stable outer electron configuration of neon. And it's important to understand that although sodium now has the electron configuration of neon, it is not neon. It is a sodium ion with a positive charge. The 11 protons that establish the character of neon still remain within the nucleus, right? It remains unchanged. Metal atoms are reactive because they lose valence electrons easily. The group 1 and group 2 metals are the most reactive metals on the periodic table. For example, potassium and magnesium, group 1 and group 2 elements, respectively, form potassium plus 1 ions and magnesium plus 2 ions. Some group 13 atoms also form ions. Ions formed by metals in groups 1, 2, and 13 are summarized in the table above. Right? And again, group 1, right, for it to become a noble gas, it must lose 1 electron. Group 2 elements, right, that have that noble gas configuration must lose 2 electrons. And those group 13 elements that can go ahead and form positive ions must lose 3 electrons to become positive. Recall that, in general, transition metals have an outer level of Ns2. Going from left to right across a period, atoms of each element fill an inner D sublevel. When forming positive ions, transition metals commonly lose their 2 valence electrons, forming 2 plus ions. However, it is also possible for d electrons to get lost. Thus, transition metals are also commonly form ions 3 plus or greater, depending on the number of d electrons in the electron structure. It is difficult to predict the number of electrons that will be lost. Right? Keep that in mind. Right? There's really no sort of trend when it comes to your transition metals. For example, iron, right, forms both the +2 and the +3 ion. A useful rule of thumb for these metals is that they form ions with a +2 or +3. Again, that's just something you want to keep in mind. Although the formation of an octet is the most stable electron configuration, other electron configurations can also provide some stability. For example, elements in groups 11 through 14 lose electrons to form an outer energy level containing full s, p, and d sublevels. These relatively stable electron arrangements are referred to as pseudo-noble gas electron configurations. In figure 7.3, the zinc atom has the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. When forming an ion, the zinc atom loses 2 4s electrons in the outer energy level, and the stable configuration then becomes what we see here: 1s2, 2s2, 2p6, 3s2, 3p6, and 3d10, resulting in this sort of pseudo-noble gas configuration. Again, here we have zinc, everything up to argon, 2 4s electrons, and here we have 10 3d electrons, add a little bit of energy, that energy, bam, takes out those 2 4s electrons, and leaves you with them 10 3d electrons, and gives you that sort of pseudo-noble gas electron configuration. Nonmetals, which are located on the right side of the periodic table, easily gain electrons to attain a stable outer electron configuration. If we go ahead and examine figure 7.4, we can go ahead and see here we have chlorine, neutral atom of chlorine, 17 electrons, 17 protons, We know it's chlorine because it has 17 protons, and here's this electron that's just kind of hanging out, When this electron's hanging out, it's going to go ahead and get adopted by the chlorine atom. And when it gets adopted by the chlorine atom, it also loses this amount of energy of 349 kilojoules per mole. And then we go ahead and get this chloride ion. To attain a noble gas configuration, chlorine gains 1 electron, forming an ion with a charge of -1. After gaining the electron, the chloride ion has the electron configuration of that of argon. An anion is a negatively charged ion. To designate an ion, the ending IDE is added to the root name of the element. Thus, a chlorine atom becomes a chloride anion. What is the name of the nitrogen anion? Let's think about that. If we were to go ahead and take nitrogen, change up its root and add IDE, it would become nitride. As shown in 7.3, nonmetals gain the number of electrons that, when added to their valence electrons, would equal 8, giving us that noble gas electron configuration. For example, consider phosphorus with 5 valence electrons. To form a stable octet, the atom gains 3 electrons and forms a phosphide ion with a -3 charge. Likewise, oxygen will go ahead and gain 2 electrons, and when it gains 2 electrons, it is going to become oxide with a -2 charge. So group 15 elements need to gain 3 electrons, so they're going to have a -3 charge. When group 16 elements, to gain a noble gas configuration, they need to gain 2 electrons, making it a -2. And again, group 17 need to go ahead and gain an additional electron to become noble gas, so they need to go ahead and gain that 1 extra one and become a -1 charge. Some nonmetals can lose or gain other number of electrons to form an octet. For an example, in addition to gaining 3 electrons, phosphorus can lose 5. However, in general, group 15 elements gain 3 electrons. Group 16 gain 2, and group 17 gain 1 to achieve an octet. Right, section summary. Well, before we do that, I want to go ahead and just kind of show you, right? Let's go ahead and look at the periodic table because there is a trend that goes on with this, right? If we were to go ahead and look at the periodic table, right, everything in group 1 is going to go ahead and form a +1 atom, ion. Everything in group 2 is going to form a group +2 ion. Everything in group 3 can form a +3 ion. Everything in group 14 can either form a +4 or a -4 ion, just depending on the circumstances. Then group 15 elements will become a -3 ion. Everything in group 16 will become a -2 ion. Everything in group 17 will be a -1 ion. And just remember that group 18 elements are noble gases and they do not like to react. All right, so section summary. A chemical bond is the force that holds two atoms together. Some atoms form ions to gain stability. This stability configuration involves a complete outer energy level, usually consisting of 8 valence electrons. Ions are formed by the loss or gain of valence electrons. The number of protons remains unchanged during ion formation.